Hello and welcome back to Differential Equation section 1.3 on slope fields, and we are also going to talk about existence and uniqueness theorem, which is one of the important theorems for differential equations, showing that solutions exist and that they are unique. So, which is one of the also important things for functions. For instance, one x cannot produce two y's. So the same thing here. One differential equation, one solution. So we're going to talk about that today. Before that, we are going to talk about first slope fields. And this is something that you may or may not cover in Calculus 3, depending on who's teaching it. It's optional. And the slope field, Calc 2. It's optional, and the slope fields are graphical way to solve differential equation. If you don't learn anything in the entire class, absolutely nothing in the entire class, you can use slope fields to draw the solution curves. You would not know precisely and exactly what those are, but you will have a very good idea of what the solutions at least look like. The rest of the course, this is the only graphical solution. The rest of the course will all be computation. Now, before we dive into differential equation, I want to go back in life to present what it means to solve equations graphically. Unfortunately, we don't teach that here. Elsewhere, yes. So I'm going to start with the good old equation x plus 2 equals 5. Ooh. Hopefully we can all solve this, all right? What would be the way to solve this? Yes, good. So you subtract 2 on both sides, you get x equals 3, you box that as the answer because 3 plus 2 is 5, and you walk away. So this is what you all know, hopefully, right? And now I'm going to present the alternative to this solution. And that is the graphical solution. I'm going to draw the good old xy coordinate plane. And I'm going to draw these two functions. You have a function f of x on the left and function g of x on the right. The left function has the y-intercept of 2, and the the slope is equal to 1. So we will have this 45-degree line that goes through 2. And that's my function f of x equals 2x. Then at 5, I am going to have the horizontal line g of x equals 5, or y equals to 5. And that is the other function. What do you see with their intersection? You see that they intersect at 3, 5, which as x-axis has x equals 3, which is your solution. You were looking for a number that fits this system, and that system is x equals to 3. All of the equations you ever learned in your life fit this description, and you do not need to know how to solve any of them using x's, y's, and moving and shoveling things around. Right? All of them. That includes exponential, logarithmic, trigonometric, quadratic, all of it, right? Hyperbolic, all. Now, another useful tool would be to see how many solutions you have for a trig equation. You are not solving it, you just want to know the amount. Maybe some of you were confused in a trig course. How do they know that we have 2 solutions or 4 solutions or 8 solutions and so on, and then you're just staring at that and you just give up, right? Well, the answer to that is, if you have an equation sine of, let's say, 2x is equal to 1/2. Now, since I am dealing with this all my life, yeah, I started when I was 1, I know immediately that it has 4 solutions just by looking at it, right? But there is a very easy way to know that it has 4 solutions. We are going to draw 2 equations that I have. First one is sine 2x. Anytime number in front of x is larger than 1, it makes sine oscillate faster. Meaning that in this case, this sine is 2 times faster than the original sine, which means it will make 2 full oscillations before it hits 2 pi. This is what you learn in pre-calc course when you learn graphing. And what that number in front of x does. You labeled that number as b, and it was related to the period. It was related to the period and frequency, thank you. And it's also related in physics to wavelength. If you want to understand what is the difference between the red and blue color, you will look at how fast the sine function moves the wave which carries the light, right? And that's the difference between the red light and the blue light, for instance, measured in nanometers. You can go consult physics if you want. So now I know also that the peak of sine is at 1. My other function is 1/2, which means at 1/2 I am going to hit a horizontal line at half. How many times did they intersect? That is how I know there are 4 solutions. Now you're going to go and chase that through quadrants and other methods that you guys know from pre-calc 2. The last type, before we start our lecture, is going to be type of equations that you cannot solve by calculation at all. Here is an example. ln of x plus 2, not absolute values, just x plus 2 in parentheses. We are talking now pre-calc 1. ln of x plus 2 is equal to 3x. This equation cannot be solved using what we call analytical method, meaning massaging these expressions with x's and y's and numbers and so on, right? The first one we subtract 2 and we get the solution. The second one we apply inverse sine on both sides and you solve the problem. Here, the only thing you can do is cry or graph. Those are the 2 options you have. Now why? Well, let's think about it. If you are to attempt and solve this, how would you kill off that ln? Obviously e, right? So you would kill this with e, and then you will finally free up that x on the left side. What have you done with the x on the other side? You buried it into e, right? Well, that's not a big deal. How can you get rid of e? ln. Yes, you ln both sides. Right? Do you see what's happening here? So, yes. So, and then we get into certain discussion of you doing the same thing over and over again, expecting a different outcome, right? Right? Right. Okay, good. So we see that the method of trying to calculate this doesn't work. Now, there is a really cool thing that you guys learned in Calc 2, and I know you love it. It's called power series. Express the left-hand side as a power series. Express the right-hand side. Well, it's already power series. It's 3x, right? It's a polynomial. And then you just have a whole bunch of polynomials. Just, chop it off somewhere, and you are going to get, a good enough answer. Good thing you all love power series because, right? So, since calculation is out of question and you don't like power series, then the only thing you can do is to draw these 2 graphs and then see where they intersect on the plane. If they do not intersect at all, equation has no solution. If the two lines never cross, equation has no solution. You just write no solution and you're done. If they intersect, whatever those intersections are, those are the solutions, which you can trace on your calculator or the software you use, and it will spit out x equals x coordinate, blah, 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 right? So in our case, what is the +2 doing in this situation? Moves it 2 units to the left. Left is for the plus. So our good old, I'm going to erase this. The good old original ln that goes through 1 will actually go through -1. And this is my ln of x plus 2. Then I have my linear function of 3x with a y-intercept of 0. It will go like this. No. It will go like this. And we see that these two functions intersect twice. We are expecting two solutions for x. One of the two solutions is going to be negative 1.9 something, and the other solution is going to be about, let's say, around 0.2. Sorry, 0.5. 1/2. Positive 1/2. Good, for x value. So now you understand that all of the functions you ever learned, and even those you haven't dealt with by now, can all be solved using graphical methods. It doesn't mean that you can forget everything you learned, but right? So now, going to our slope fields, we are going to learn the method that you can use to solve differential equations by drawing out infinitely many, or in our case, human case, will be finite many, little slopes of the lines that will give you a field through which you get to draw your lines. If you ever played with magnets and little pieces of metal and so on, you know when you put the magnet, they all arrange in a way where the magnetic field lines go. We're going to do that on a paper without magnets for every differential equation. So they give you a couple of complicated equations. Slope fields are things that you have seen hopefully in your calculus book before. It is the standard x and y graph with about 100 of these little tiny lines which would guide you to draw the blue solution lines through the what we call slope field. Each one of these little tiny lines is a slope that you get to draw at the point you pick in the xy plane, and then we call it a field because that happens at each individual point. Yes, we are picking some of them, not all infinity of them, and then that draws the field which guides which way the lines will go through. So let's just pick one of the homework exercises. Here, problem 6 is perfect. And just dive straight into, there's no theory for this. It's just a collection of tiny slope lines. Differential equation is dy dx is equal to x minus y plus 1. This is a nasty little critter of the equation because it's not separable. There is no way to put y's on one side and x's on the other. If you move plus y to the other side, then your x is stuck in a denominator, right, of one of the two terms. So you can separate this. It looks really like nice, but no. So a way to solve this would be, we have other methods. Trust me, power series method is awesome. But hold on, we're not going to do that on day 2. We can draw the slope field. So let's make graph as large as possible. Good thing you all have a square paper, so this is all perfect. Otherwise, it will be a mess. And it's very important to draw big. Even if you are used to drawing small, this is the time to draw big. Yes, that's why I said it.
Yeah.
Now, what I'm going to do is I'm going to pick a slope of whatever. So let's pick slope 0. What kind of slope is slope 0? It's a flat line, horizontal line. So pick m equals 0, which is dy dx. Do we all understand it's dy dx? Perfect. So for the slope you picked, once you plug that into your equation, you will get 0 equals x minus y plus 1. That's a step that usually confuses people. I'm not sure why, but plug it in. You pick the slope and then plug that slope in instead of the differential equation, instead of the dy dx. And now just solve this, and what you get is y equal x plus 1. A linear line. Are we all happy with this one? Beautiful. Now, we are going to draw lightly dashed x plus 1, y equal x plus 1 linear line, lightly dashed. All right? Because that's not our solution. So I'm going to pick a gray pencil for this. And I'm going to go to my plus 1 and draw dashed line like this. Now, we actually don't care about that line. That line is our guide. What's happening at every point of this dashed line? A little slope is 0. So you get to now use your regular pen, the same pen you used for x and y axis, and draw little horizontal 0 slopes. Anywhere, but they have to follow this line, and depending on your OCD, right, you might have each one, right, meet this, that's gonna be that. But this is your slope. So this line, the gray line is called the isocline, and it's, whatever. We have these little slopes, that's what we're after. Now, you are going to change your value that you pick. What do you want? 1, -1, 2, -2. Do you want pi squared over 6? I don't care, right? Whatever you pick, whatever number you pick, you will plug it here and then solve, graph the gray line, and then use whatever number you pick as a slope, right? So the next slope I am going to pick is going to be 1, right? So the next one, I'm going to pick m equals 1, which is dy dx. Now, what I'm going to do here on the side is I'm going to put a red little line to denote what it means for a slope to be 0. And over here I'm going to put little 45 red line, which is what it means for a slope to be 1. Once you get your gray line, along that gray line, you get to put these kind of lines. Not that one. That's a 0 slope line, these black lines. You are going to now, once you get the gray line, it will be whatever, because you have a 1, it's y equal x, right? You will put these. So let's go and figure out, plug our slope for dy dx, that's 1 equals x minus y plus 1. So y equals x is our isocline here. So I get to draw 45-degree line lightly through the origin. And along that gray line, I'm going to fit a couple of these 45-degree slopes, little slopes, right? Which are now actually coinciding with my gray line because they have the same slope. What we already see, I'm going to erase this, but what we already see is that our solution curves will do something over here, I don't know what, and then they're going to come in and they're going to bend this way. Try to think of channeling the water through these and they're guiding. You see, like, wee, like that. You see that? This is what slope fields are going to do. Now, you can't just draw 2 lines because you see what I did here, right? Because I still don't know what's happening on that end. So you cannot draw 2 or 3. You need like 5 or 6 of these to have somewhat good idea of what's going on, right? Well, welcome to graphical solutions. Remember, to graph y equal mx plus b, what do? Y-intercept and draw the slope. You're done in 2 seconds. Or calculate a couple of points and then connect them. Takes time, right? Well, let's go. Pick -1. Pick -2 and +2 and call it a day. Why is my battery running low? It's plugged in. Okay. +2. Now the slope of -1 is a reverse 45. We have a line x plus 2. So this was x plus 2, this was x plus 1, this is just x. And now I have reversed slopes. You know what you're supposed to do, so just on your own pick -2, pick +2. Let's have 5 lines, and then we're going to snake through solution. Now, -2 slope is steeper than -1. You don't have to be perfectly right on it, but so instead of connecting the two edges in a square, I sloped it more. Okay, so I have 5 of these, and what I believe is happening without doing any more of these is I believe that the functions are coming in from this side and bending inwards to follow y equals x asymptotically. On the other side, what I'm thinking is happening is probably it's happening the opposite. I think it's doing this on the other. I don't know. I need more lines on the right. I need to pick 3, 4, and 5 maybe to add extra lines. And I don't know. When you don't know, you add more lines. All right. Now, this was one of the homework problems, problem number 6 in 1.3. So let me see if they have anything on it to confirm this. What they have is exactly what we have. They drew only one line on the left-hand side. They did not draw any lines on the other side, where I don't know what's going on, but they have a full slope field, and they're asking you to draw a couple of lines with a random startup point. So what they give you in a homework is they give you a point right here and say, what does the solution through that point look like? And you're just supposed to snake the, there we go, snake the solution through that point and follow the flow of the field, right? The way the leaf follows the way the wind creates the field for it, right? The leaf has to follow whichever the way the wind blows. Right? You know what I mean. And that's slope fields. I hope you're not disappointed. There is not much on that. Let's write existence and uniqueness theorem. Yes. Okay, next time I'm going to ask Da. Because I don't know if yes scared you or did I look threatening or something as I went yes? Maybe I should go yes? Oh, okay. Cool. All right. Wow. Theorem 1 on page 22. Existence and uniqueness of solutions. This is still the same lecture, right? This is the last part that we are discussing here. Obviously in red.
Oh, in red.
He gave in. So.
That's not going to happen.
How about if I give you the purple one for mine?
Now you need some purple?
No, I'm good. I'll put a star next to it.
In red?
No.
All right, so here we go. This is one of the two cases when you are going to see partial derivatives from Calc 3. Suppose that both the function f of xy and its partial derivative dy of f of xy, the notation you used in calculus course was just partial of y. Okay, that was your notation from Calc 3. R continuous on some rectangle R. That's just the space that will box in your solution. Please remember, solution for a differential equation is a function y equal f of x, right? You draw that on xy plane, which means you can draw the box around it, right? At least around a part of it. You can draw a box, which is a rectangle. So, continuous on some rectangle R in the xy plane. That contains the point AB. In its interior. Then, for some open interval I containing the point A, the initial value problem dy dx equals f of xy with initial point y of a is b. That's your point AB. Easy. Has one and only one solution. That is defined on the interval I. a lot of words here. Where is your existence? It's right here. And where is your uniqueness? It's right there, right? There's your existence and uniqueness in 5 words, right? The rest are conditions that have to be satisfied in order for that to kick in. What is the meaning of this? The meaning of this is that when we talked about that word problem for population, where the change of population in time depends on, is proportional to population, well, that word problem, which you transferred into differential equation, had a single and only one solution, which was p equals p0 e to the kt. That's what it means. It doesn't have 3 different functions, and then you have to pick one, right? Or be lucky to get the one that works, right? So if the solution to x plus 2 equals 5 is x equals 3, and that's unique, the solution to differential equation is a function. That function better be unique. You're not getting 7 different functions, right? And then pick one. One equation, you could have 2 solutions. Quadratic function has 2 solutions, right? x1 equals blah, x. We are going to have that for a second order, right? But you're not going to have 15 of them. First order differential equation, 1 solution. Second order differential equation, 2 solutions. So this over here is going to have sine blah 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 plus cosine blah blah blah. This one is going to have sine hyperbolic plus cosine hyperbolic, also expressed as e to the positive exponent plus e to the negative exponent, right? And we'll combine those solutions. So the amount of solutions you get for the differential equations will be the same as the order of differential equation, which is following the same concept that you had with the polynomial. 7-degree polynomial, 7 solutions. Some of those 7 might be complex, but they still exist and they're there, right? So now for the existence and uniqueness theorem here, if your differential equation is continuous, we just had y prime is equal to x minus y plus 1, I believe, or whatever. This fits this definition. Is this a function of x and a y? Perfect. There is your calculus 3 definition here. And then, you pick a random point somewhere. Remember what I said in the last lecture when we talked about the plus c? That when you have initial point, you can calculate the function that goes through that point, and you will not have plus c anymore because you will calculate the value for that c. So unique solution means that once you have that point, only one function out of all of the infinity of those plus c that are stacked on top of each other, only one of those infinitely many functions is going to hit through this point. Since there is something that goes to that point, that's existence, and only one goes to that point, is your uniqueness. Cool? I hope so, right? So that's the theorem. And you see that condition is that the partial derivative is continuous and function is continuous. Now, partial derivative being continuous, that's actually calc 1 continuity because that would be only one variable, right? Well, it could be 2. Because this could be x cubed minus y squared. And then, so you could have this, in which case you would have multi-dimensional derivative. So derivative needs to be continuous, function needs to be continuous, which means that for this, you need to know your continuity definition from calculus. And that was what? What were those 3 rules that you need to know?
Decreasing, positive.
You are now talking about integral test.
the limit?
The limit exists.
They have to be equal, positive.
That's the third rule. What's the first one? You gave me second and third. What's the first one? First rule for the continuity.
Oh, doesn't the derivative have to be the
No derivative.
Doesn't the function have to be smooth?
Function has to exist, not smooth. Exist. So, and now we know the function exists because that's given, right? So, function exists, the limit has to exist, and then those two values you get have to be the same for the third rule, right? And then you have that. So, the type of a problem here is they give you a differential equation, and they say, is the differential equation, does it have a unique solution? What do you need to do? You just need to crank the limit, make sure that the limit exists, make sure that it gives you the numbers that you get, and then if that works, it's great. If any of those two fail, that means that it doesn't have a unique solution, right? And we know that because you can still solve the equation for a circle. It's not a function. There's no uniqueness. You can still solve it, right? So we have to kind of separate those two worlds. So it's not that if something cannot be solved in the realm of our theorem, it's immediately, cast off the world or the galaxy, right? The circle still exists. It's not a function. Don't panic, right? We can still find the two values. It's not a function. So it's going, and then we also have discontinuous functions, 1 over x, right? We don't throw in a garbage because it's discontinuous at 0. We can still use 1 over x. We can't use it at 0 to create something, right? Because it would explode there. But everywhere else, you can use it, right? So those are the things. So, the first example, differential equation they give you is just y prime equals negative y. The derivatives are negative 1, right? Negative 1 equals negative 1, done. Because you just, by figuring out the derivative and the limit, right? You immediately know it's continuous and derivative exists. So it's continuous and derivative exists, so you can do the continuity and everything, and it's immediately unique solution. And that's the one we can solve and show what the unique solution is because it's a separable, easy equation, right? So as one of the examples, dy dx equals negative y. And for this one, we have this part here, which is labeled as fxy equals negative y, and your partial derivative in respect to y. This is when your Calc 3 kicks in for the first time, is negative 1. So this is continuous because it's polynomial. That was the theorem which says polynomials are continuous, sine, cosine continuous, exponential, logarithmic continuous, right? And this is also continuous because it is a constant function. So they are both continuous, and you can pick a point A, B, and you can find the solution. Now, luckily for this cheap problem, we can actually solve it and show what that unique solution. So this over here says yes, exists plus unique. I'm talking about your final exam problem right now. This is a learning outcome. A problem of similar kind with a different mess over here is going to be there 100%, okay, in 4 months. So I hope you change the color on this problem. You always have red ahead at hand. Let's do the separation of variables because we can. We'll have dy over y equals to negative dx. I'm going to leave a negative. Just move the y. When I integrate both sides, which I'm going to add this red integral, I will have ln of absolute y to be negative x plus c. Then I am going to e both sides and get y equals e to the negative x, and then I'll just say times e to the c, which will give me y equals, let's say, a e to the negative x. And there is your unique solution. It exists. You see it, right? It's right there. So it exists, but also by the theorem, it's guaranteed that it's unique, so no other solutions fit. You can also differentiate this and then plug into differential equation to show that this is a solution. On your first exam, at least one problem will say, prove that following function is a solution to given differential equation. I give you the function, give you differential equation. What do? Well, you differentiate and plug in, right? So to check, you have your y prime is equal to a e to the negative x times the chain rule negative 1. So y prime is negative a e to the negative x. And now you plug in into y. Our differential equation was y prime equals negative y. So instead of y prime, you put negative a e to the negative x. Then you copy the minus. And instead of y, you put a e to the negative x. And you see that the left is equal to the right. Right? Just like when you plug in 3 into x plus 2, you get 5 equals 5. Over here, you get same functions on both sides. So this is the solution to the problem. You are going to have a couple of examples of your homework. You will do the homework. And if you get stuck, you will ask questions, I hope. Right? Okay, let's cool off. And then, yes? I'm sorry? So we are checking if this is a solution, right? I didn't box it because I wasn't sure, because I care, right? So I want to check. So to check, I see that I need to plug in, this is my differential equation. I need to plug derivative of the function I found on the left, and I have to plug in the function that I found on the right. So that's what I'm claiming is a solution. Then I find its derivative, and then I plug that derivative into derivative, and I plug original function into the function. And if they turn out to be the same, then 5 equals 5, right? And we're done. Yes?
And why is this system unique? Why is it unique?
Because the conditions from the theorem were satisfied.
Okay.
Right? So you have to learn the conditions from the theorem, okay. Right? So once you have the function f of x and the partial derivatives are continuous, yeah. Okay. We're good to go. Sometimes if it's difficult, yeah. Right, you have to involve those 3 rules. Depends on how spicy the problem is, right? So polynomials, ln, e, sine, the basic functions in a vanilla state, yeah. You can just quote the Calc 1 theorem. But if you get, x squared divided by x squared plus y squared, right, then it's going to be 3 rules. Is the limit, does the limit exist, and so on, right? So it's all Calc 1 and Calc 3 work, right? Unless they're basic functions like in this example. So you will see, and if you in the homework, and then you can always ask. I'm not going in.
So are points A and B supposed to just be arbitrary, just something you choose to fit within that rectangle?
Well, the points A and B, since you were baking in the class, the point A, B is when you test the temperature. That's what the points A and B are, yeah. Right? the point AB will always be from your physical observation of the system, right? So the point AB will be your measurement.
It's the epsilon.
We call it initial condition.
Okay, yeah, just
Yeah.
to smooth it out. Okay.
A data point along the line. One of our initial conditions was when we picked the population from 1900.
Yeah.
So we had the X, which was a T, 1900,
And then wherever you
and
end
then
up.
1.6 or 7 billion, whatever it was. Yes?
Okay, I got two questions. First of all, like I get the way it exists, but how can you tell if it's unique or additive?
Again, it's in the theorem. The theorem says if it's continuous on the f of xy, which was this, and if it's continuous, the first derivative, partial derivative in respect to y, then it's both unique and it exists and it's unique. Okay? So if those hold, then you get to conclusion. Now, if you're asking for the proof of this, the way to prove this theorem, right? So there's one thing to prove it and one thing to use it, right? You asked me to use it. That means I just look at these two and I'm cool, right? Now, you might have a follow-up question. Why does that work? In which case I have to answer, you have to prove the theorem by assuming that there are two different solutions, and then when you follow the calculation, you will come to conclusion that that's impossible, which means that the two solutions were the same solution. Okay? Cool.
Can you scroll down for a minute?
Of course. Free of charge. Now you did not specify how long the moment is, so any other questions? Yes.
For this problem, how did you know e to the c was going to be a?
Oh, I just picked anything.
Oh, okay.
What is your favorite letter?
I don't have one.
There's 26.
So why are you bothering my A then?
I was just wondering if there's a certain reason.
Okay, so if you come up with a favorite letter, we'll use your letter. Until further notice, I'm going to use A. Cool? So e to the c is going to be A or P0 or whatever, V0,
Okay.
whatever the application is asking us,
Yeah.
right? In general, we just use A,
Okay.
also capital K, and when you integrate, it's plus C.
Okay.
You can use whatever.
Sounds good. Didn't you know? Haven't you seen it before?
No.
I know you.
All right, we're going to take about, wait, this class ends at
1250.
12:50. Okay, so let's take about 120 seconds of break, and then we're going to go through 1.4. It's separation of variables. So technically, we're just going to review integration, right? Again.